Hi, my name is William Bushy, and this is Lab 2 for Physics 2. So this lab was to study how objects can become polarized and how the resulting charges can create forces that may either attract or repel other charged objects, and then figure out how big the magnitude of that charge is. So formulas we'll be using and just basic data. The mass of the tape pieces was 0.002032 kilograms, which is roughly a fifth of a gram. The height of suspension of the tape was 0.15 meters. The electric field formula is Q times K over R squared to the R hat, or times R hat. The electric force is Q2 times E, so you take the above equation and multiply it by the second charge in play. K in this case is 1 over 4 pi E naught, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared. And the force of gravity is mass times gravity. Gravity in this case is negative 9.81 meters per second squared. So the methods: 8-inch pieces of tape were folded so that 1-inch handle on the end was available so that you could hold it without getting your hand stuck. One piece was laid flat on the table and then another on top and then rapidly removed to create a charge. This was suspended from 2 cups of equal height. A third piece underwent the same process as the second, and when brought underneath the second piece, the strips of tape repelled each other. So here is the code we used. And in this case, the charge was found to be 1.4 times 10 to the 7th coulombs. And the mass was 0.002032 kilograms, as stated earlier on. And let's see. Here's the video. Here is the process of the tape being charged and then suspended. So the results, the tape that was suspended was moved up 0.5 centimeter by the electric force, and so that will be our radius r in this case for the electric field equation. The force of gravity was negative 9.81 times 1/5 of a gram, and because it was held stationary once the charge was introduced underneath, at that point, with that radius, gravity must have been equal to the electrical force. So once you sort out the equation, you get the square root of mass times gravity times the radius cubed divided by k is q, and q in this case ends up being 1.4 times 10 to the 7th coulombs. And the charge length per unit length on the tape was 1.4 times 10 to the 7th divided by 1/5 of a gram equals, or 0.2038 meters equals 6.9 times 10 to the 7th coulombs per meter. So using the same data from the previous experiment, but treating it as a collection of charges per tiny fraction of length dl, allows us to better envision a number of fields acting together to achieve the final results, as opposed to a single point charge where we generalize the results. If we treated the tape as a point charge, the field would only be applicable in one particular spot, and it would not account for the overall movement of the tape. The results differ because this experiment takes into account the charge per unit length of the tape, which treats the experiment as a sum of very small parts. The second experiment is much likely more accurate. Thank you.